Okay, we're continuing on here, chapter 13, I think. And last time we talked about equilibrium, and we talked about the equilibrium constant, and we talked about two equilibrium constants. We got Kc and Kp. They both are really the same. Really, all K values there are equilibrium constants. C means we use concentration. P we means we use not products. We use pressures. And basically, to calculate our equilibrium constant, it is the concentration of our products over the concentration of our reactants. Unlike in kinetics, we do use the actual coefficients from the balanced equation as the exponents when we do that. So again, in general, here, RK here would be the concentration of C to the C, D to the D divided by A to the A and B to the B in this case. And obviously, as we talked about, typically speaking, Kc, you're going to be using molarity is typically what you want to use for usually any type of equilibrium calculation that involves pressures. We do use usually atmospheres as the unit. And remember that if we do have a large value of K, that means when we reach equilibrium, we would mainly expect sort of products to be present. Just mathematically, we have a large number on top, which is our products, divided by a small number gives us a larger number. So we expect more products there at equilibrium, and vice versa. If we have sort of a small value of K, um, that means that we would expect more reactants. And again, just mathematically speaking, we have a larger number on the bottom and a smaller number on top. That's going to yield us a small K value in this situation. Remember, K is one of the few things sort of in chemistry that we actually do not usually use units associated with. So it is just a number. We also saw a relationship that allows you actually to go way ahead. I've gone the wrong way there. Just trying to get done. Go back that way. There you go. So we saw a relationship between these two guys here, and that is the Kp is equal to the Kc RT delta N. And R is our gas constant, is the one that we use in the ideal gas law, 0.08206 or 21. Temperature here doesn't even Kelvin. And obviously, that's our Kp value and our Kc value. The one thing we talked about that's really important is this delta N, and that is the change in the number of moles of gas molecules. So we take the moles of the gas molecules on the product side minus the moles on the reactant side. And as we talked about, it's really important to make sure you do that, because if you just take the difference, you may actually get a negative number here. And mathematically, again, if you have a negative number there, you're going to do something different, obviously, than it was, say, 1 versus -1 for your end value. That's a different sort of mathematical thing. So you just don't want to take the difference. You do want to do products minus reactants. And again, if you get a negative, obviously that's important towards our calculation here. The other really important thing we talked about with equilibrium expression is only pretty much things that are aqueous and gases get included. Anything that is a solid or a liquid is not included. So when you're writing those expressions, we are only looking at things that are aqueous and gas. Anything else that's in any other state, you just basically leave off um, in that situation. Any questions on any of that stuff there from last time? All right. I feel like I didn't go far back enough there, maybe. All right, so I think this is where we were, I think. All right. So, as we were talking about before, solids and liquids, again, are really not involved in equilibrium. You can kind of see there, they're just kind of sitting there. They're not really participating per se. Again, in order for these guys to sort of participate, they would either have to become gas molecules or it has to become aqueous and start moving around and sort of participating. So we really don't worry about those things in that situation. Um, so let's take a look at this one. I don't think we did this one, so why don't we give this one a go? Consider the following equilibrium at 295. The partial pressure of each gas is 0.265. We're looking for both the Kp and Kc value. So take a few moments there, see what you come up with here. Okay, let's take a look, see how we're doing. So obviously in this case, we're given some pressures here, and obviously these are some equilibrium partial pressures. So Kp would seem like the logical choice here to calculate since we have really all the information we need. So the Kp here would be, again, our products, which is the partial pressure of NH3 times the partial pressure of H2S. And once again here, with this being a solid, we are not going to include it in the equilibrium expression. That means for our Kp, since they are both 0.265, we're basically just going to square that there. And that's going to get us here 0.265, a little squared. It's going to get us 0.0702 as our Kp value. Now that we have the Kp value, we use that formula we just saw there to kind of convert to our Kc, where the Kp is equal to the Kc RT delta N. In this case, our temperature is already in Kelvin, so we're good to go on that. We obviously just calculated Kp, so we got that. R is a constant. And really, the only thing we kind of need here is our delta N. So our delta N in this case is, again, only the gas molecules here. So we got one gas molecule there and two on the product side. Minus, again, this is a solid, so that is minus 0, which gives us a delta N of 2 in this case. Popping in our numbers here, 0.0702 equals Kc. 0.08206 times my 295, and that's going to be squared. So just kind of cleaning up the right-hand side there, what's in the parentheses, 0.08206 times 295, and then I'm going to square it if I can find that on my calculator here. There it is. And that's going to get us something like 0.0702 equals Kc. Then we got a 586.0127. We're obviously going to divide that now to the other side. And if we do that there, that will give us our Kc value of about 1.20 times 10 to the minus 4 in this case. Yeah. Any questions on those calculations? Once again, as we sort of talked about last time, they oftentimes Kp and Kc will not equal the same numerical value. It is possible that they can, but most of the time they will not. But they both should also tell you, again, the same sort of thing about the reaction. We would consider both of these values, the Kc and the Kp value, to be considered a small value of K, since it's less than 1. And we would expect mainly reactants in this particular situation. Yeah. Any questions? So like I said before, they really should agree. You shouldn't really get a large Kp and like a small Kc. They both should either be both small or both large, and kind of agree in that sense. Any questions on calculating Kp or Kc? Okay. There's our intro. All right. The next thing we're going to actually talk about is what happens when we need to manipulate equations, these reversible reactions that have a K value associated with it. So there could be a situation, and I guess I'll relate it to like Hess's law that we talked about there a little bit earlier, and that you did last semester, where you take all these individual sort of equations, kind of put them together, switch them around, and maybe multiply or divide by numbers, and then put them together, add them together, and you get this overall reaction that you're looking for. That also does happen with equilibrium type reactions. So again, a reaction may be a result of multiple steps rather than just one individual step. And it may be some situations where you may have, for example, a reversible reaction with an equilibrium constant, and maybe they want to know what the K value would be for maybe the reverse of that reaction, or if you multiplied it by 2 or things like that. So if we take these two equations here, A plus B goes to C plus D, and C plus D goes to E plus F, and we do add these guys together. Again, anything on opposite sides of the arrows will cancel out, so these guys are going to cancel out. And that's going to give us an overall reaction here of A plus B goes to E plus F in this case. And if we were to write an equilibrium expression for this reaction, K would equal E, concentration of E times concentration of F, divided by the concentration of A, and the concentration of B would be the equilibrium constant for the overall reaction. So ultimately here what we did is we added those two individual equilibrium reactions, and they both had K values. And how we get to the overall K value here for our combined is we actually multiply the two K values together. And if you were to multiply the K value for the first one and the K value for the second one, what you would see is the C's and the D's would cancel, and you would be left with the overall equation here that we got for the overall reaction or the overall expression. So if you have two or more sort of individual reversible reactions that you're adding together, and you want the K value for the overall reaction you get when you do that, you actually multiply all the K values together. So it is different than what you do with Hess's law where you add things. Here we don't add, you actually multiply the K values together, and that will give you the proper K value for the overall reaction. Any questions on that there? I almost wrote it in the exact same spot. That's not bad. Now, another very common thing that you sometimes will do with these reactions is maybe the way the reaction is written, you don't want it that way, but you want to reverse the reaction, which means, again, your reactants are going to become your products are going to become your reactants in that case. So if we take a look at what happens in that situation here, if we have an equation such as we do here on the left, and we wrote the equilibrium expression for it, it would be the concentration of NO2 squared divided by N2O4. And again, that would be, for example, the value that comes with that. If we reverse this reaction, the equilibrium expression would be the concentration of N2O4 over NO2 squared. And again, this is because basically our reactants become our products and our products become our reactants. So how that affects the K value is you would actually take 1 over the K value. So unlike in Hess's law, we don't change the sign here. It's actually 1 over the K value. And that would give you, in this example here, 216. Now, when you are looking at a K value, it is specific for obviously the temperature, as we talked about, because temperature is the one thing that can affect the K value, but it's also specific for exactly how that reaction is written, who is on the reactant side, who is on the product side. So if I said the K value for this reaction is 4.63 times 10 to the minus 3, I am specifically talking about how the reaction is written on the left-hand side. I am not talking about the reaction on the right-hand side, even though they're the same things, they're just reversed. If I say the K value is 216, I'm talking about, again, the reaction specifically, how it is written there on the right-hand side. So when you do see that K value, it is specific for exactly, who's on the reactant side, who's on the product side, and obviously it's specific for that temperature as well, as that can affect it. So a couple of things here in terms of manipulating K values. If you do something to the equation, you add a couple equations or more together, you just need to multiply all the K values together to get the overall. If you need to reverse a reaction, you're going to take 1 over the K value for the new reaction that you get when you reverse it. A couple other things that you can do is if we had a reaction such as A plus B goes to C plus D, we could write our equilibrium expression once again, C and D divided by A and B. And let's just say, for example, I did not need just 1A, but I needed 2A's. And I was interested in what would happen if I had 2A's. If I had 2A's, I would need to basically multiply this entire reaction by 2. And when I do so, I get 2A plus 2B gives me 2C plus 2D. Now, if I write my equilibrium expression for this one, it would be C squared, D squared, divided by A squared and B squared. What is the difference between these two? It is squared. Yeah, so the second one is squared here. So I multiplied by a common number of 2. What happens to my k value is I need to square it. I do not multiply my k value by 2. Again, not like Hess's law type of thing, not like energy. Here, what happens is if you multiply by a number, you take the k value to whatever that number is. If I would have multiplied by 3, I would take the k value and cube it. Yeah. And if I multiply by 4, take it to the fourth power. So whatever you need to multiply a number, an equation by. So if you multiply, you take the k value to that number. Yeah. Whatever that number may be. Now, obviously, the last thing that you typically would perhaps need to do to manipulate some of these equations is instead of multiplying by a common number, maybe you need to divide by a common number. So if you have to divide by a common number, I'll just take the second one here. Let's just say I want to divide this whole thing by 2. That would put me back to my original equation I had on top there, which would be this. And that would also put me back to my original K expression here. Now, in comparison between the second guy and the first guy, what is the difference between those two K values? Is the square root, right? So I basically divided by 2. Again, I do not divide the K value here. It actually ends up being the square root of the K value. So you would basically square root that K value. By the way, it works kind of the same way as multiplication. So if I were to divide by 3, I would take the cube root of it. If I divide by 4, I'd take the fourth root and so forth. So kind of the same idea. If you divide an equation, you're by a number, you're going to take the k value to that number, the root of it, basically, to that number. So those are the 4 ways that you oftentimes can manipulate these equations. And again, basically, there's kind of 2 types of questions that you would use this for. Again, if you're given sort of a stepwise sort of formation of an overall reaction where each step has a k value, that's one way you do it. Or if you just have an equation with a k value, and maybe they wanted to know if you manipulated it, then you would have to keep track of what you adjusted. So why don't you try one here? Let's say we wanted to know what is the k value of this equation based off of what is below here. So take a All right, let's take a look at this. So again, my approach usually to these type of problems where you're trying to build an overall reaction from individual reactions is, just keep it simple so you don't confuse yourself, right? So really, there's a whole thing about this is just to get everybody on the correct side of the arrows, basically. So when I look at the top here, where I want to end up, I see E and F is on the left-hand side. Here I see E and F is on the right-hand side. So I clearly know I do need to reverse that reaction to get them on the other side. In addition, I don't need 1E, but I need 2. So I also need to multiply it by 2 as well. So I'm going to reverse the bottom reaction. And I'm going to multiply everybody by 2. And that's going to put everybody in the right spot. Now, the important part of this is I do need to kind of keep track of what that does to my K value, right? So first off, I reversed the reaction, which means I need to take 1 over the K value, right? And that was for the reverse move there. And then I also multiplied it by 2, which means I then need to do a little square action on that as well. So that's the important part. You want to kind of keep track of how you're manipulating them. Obviously, I look over here on the equation I'm looking for. I got A and B on the right-hand side over here. A and B are on the left-hand side, so I know I need to reverse that. Actually, only need 1 A and B, so that's good. So I'm going to reverse the top reaction. And that's going to put my A and B hopefully in the right spot. Now for the top reaction, and I also should probably grab the right number on that first one there, not the K value for the top one, and maybe use the right number would be good. And that first one was 20, since that was the second equation we used there. For the first equation, all we did was reverse it. So we're going 1 over 100 in this particular case. Now I think we're in business. So that should yield us, since we're out of equations, the correct one that we want. The two C's will cancel, the two D's will cancel. Everybody on the left-hand side will stay there. So that's 2E plus 2F goes to A plus B, which is the equation that we are looking for. So now in this case, we're looking for the K value. And I'm just going to call this K1 and K2 here just for numbering. Remember, though, that when we do add equations together, what happens to the K value is we multiply them. We don't add them. So in this case, to get to what we need, we're going to actually multiply those two K values together. However we want to do that, if we want to kind of get a number for each of these, now that I got everybody hopefully in the right spot there, 1 divided by 20, do a little square action on it. That's going to give me something like 0.0025 for that one. And then 1 divided by 100.01. So we're basically going to take 0.0025 and times it by 0.01. And that will yield us our K value for our combined one. Feels like a lot of zeros to count. I'm just going to go scientific notation here. 2.5 times 10 to the minus 5, I think, in this case. Any questions on that? So you just want to kind of keep it simple, get everybody on the correct sides, and you just got to kind of keep track of what you did and how that affects the K value. Any questions on that there? Okay, I'm going to try another one here. All right, so we're looking for the bottom reaction, what the K value would be based off of the top two. See what you come up with. Keep everybody on the correct size. So I see in my overall reaction here, I need N2 on the left, and this is the only equation with N2, and it is on the left, so that's good. But I need to end up with two of them, and I have a half there. So that is going to require me to do some math there. I think that's multiplying by 4 there. I think we'll do that for it. So we do have to multiply everybody here by 4. And when I do that, that's going to end up with 2N2 on the top one. That's going to be 12 divided by 2, which is 6H2. And that's going to be a 4NH3. Once again, in this case, because I multiplied this by 4, how that affects the K value is, again, we're not going to multiply it by 4, but we're going to take it to the 4th power. So again, that's the important part there. That then means I need H2O on the left, which I do have here. But once again, here I need 6 to end up with. I only have 2. So that's going to require me to multiply this guy by 3. And if I do that, that's going to give me 6H2O goes to 6H2 and 3O2. And again, what I did in this case is I multiplied by a common number. So once again, going to take it to that power, not multiply by 3. I'm out of equations, so hopefully I did this right. So let's see, we should have 6H2s go away. And I think that is it. So we got 2N2 plus 6H2O on the left, and 4NH3 and 3O2 on the right. Again, our K value, I'm just going to arbitrarily call that one 1 and 2. The K value for our overall reaction, because we added it together, K1 times K2. So we take 411 and we take it to the 4th power. That's going to get you something like 2.85 times 10 to the 10 and 0.345 to the 3rd power. Looks like that will get you something like 4.11 times 10 to the minus 2. Once again, not adding those together, but multiply them together. And I'm just going to take the whole number of each of those on my calculator here and multiply them. And that is going to get me a 1.17 times 10 to the 9 here as my equilibrium constant. Yeah. Any questions on manipulating equilibrium reactions? So again, the key is really just to keep track of what you did and try not to do like the Hess's law thing. And that's a super common error people do. They multiply by that number. They want to multiply the K value. They divide by the number. They want to divide the K value. And more commonly as well, when they reverse the reaction, they want to just change that to a negative. So remember, this is a little bit different what happens as you manipulate those equations. All right. Well,